The Monty Hall problem is a probability puzzle based on a game show. The setup is simple. There are 3 doors. Behind one door is a car. Behind the other 2 are goats. You pick one door, but it stays closed. Now the host, Monty, steps in. He knows where the car is. He always opens one of the 2 doors you didn't choose, and he always reveals a goat. Then he gives you a choice. Stay with your original door, or switch to the one remaining unopened door. The question is simple but deceptive. Should you stay, switch, or does it not matter? The correct answer is that you should switch. Staying wins with probability 1/3. Switching wins with probability 2/3. Here's the cleanest way to see why. When you first pick a door, there is a 1/3 chance you picked the car and a 2/3 chance you picked a goat. That part is not controversial. Now split into 2 cases. First case, you initially pick the car. This happens 1/3 of the time. Monty opens a goat door, and if you switch, you lose. Second case, you initially picked a goat. This happens 2/3 of the time. Monty is forced to open the only other goat door. The remaining unopened door must be the car, so if you switch, you win. Switching wins exactly when your original choice was wrong, and your original choice is wrong 2/3 of the time. That's the entire result. The most common objection is, after Monty opens a door, there are 2 doors left, so it's 50-50. That intuition ignores how the door was opened. Monty's action is not random. He is guaranteed to show you a goat. Seeing a goat doesn't rebalance the probabilities because it was certain to happen under the rules. Your original door keeps its 1/3 chance. The remaining 2/3 probability was on the pair of doors you didn't choose. Monty removes one losing door from that pair, so the entire 2/3 shifts to the single door that remains. If this still feels uncomfortable, scale the problem up. Imagine 100 doors. You pick one. There's a 1% chance you picked the car, and a 99% chance you didn't. Monty then opens 98 doors, all goats, leaving just your door and one other. Staying gives you a 1% chance. Switching gives you a 99% chance. Nothing essential changed from the 3-door version. The deeper lesson of the Monty Hall problem is not about doors or goats. It's about conditional probability. Probabilities depend on how information is revealed, not just on what you see at the end. Ignoring that process is why this problem feels like a paradox, even though the math is straightforward once you track it carefully.